Today what I'm going to talk about is, so there's a bit of geometry, but it will remain at the level of motivation. It's mostly something about combinatorics. And it's a joint work with Boris Bourg from Carnegie Mellon. And so if I say anything that you don't understand, you should stop me, because everything should be accessible from first principle. Okay? The basic object I want to look at are set systems. You may know them as hypergraphs. You may know them as subsets of the discrete cube. Okay, so you may know them as range spaces. And all these words always mean the same thing. It's just a collection of subset of a given set. Okay, so you fix a set X, a ground set, and your set system H, so H is a set of subsets of X. So this is a very simple object. It turns out there are interesting things that can be said about it. So one example, if you're interested in graphs, one example that we may discuss a bit later is, given any graph, you could consider the set system where you take the vertices and the edges. So given a graph, you can think of it as the set. So the ground set is a set of vertices. And now your H is all V in X, union all UV, where these two form an edge in your graph. Okay, so singletons and pairs. If you're doing some geometry, and if you're trying, for example, you have a set of points in the plane, and these are users for your cell phones, and you want to place antennas so that you cover every user, and your antennas, they all, no matter where you place them, they have a radius of 1 kilometer. Okay, so, and what you will be interested in is not quite the geometry of your point set, but you don't care about the exact position. What you care about is what are the subsets that can be covered simultaneously by a disk of radius 1 kilometer. So studying this problem, so a covering problem in computational geometry, so it reduces to a hypergraph problem, where your hypergraph as X is a set of points, and H, for example, are all subset of X, such that there exists a disk of radius 1, disk D, such that S is equal to D intersected with X. Okay, so you look at this hypergraph and it tells you more or less what are the possible solutions. And it's very natural to look at half planes, disks, unit disks, and so on. Now, one of the things we care about in computational geometry is to estimate orders of magnitude. So when we have such a hypergraph, if I tell you that you have endpoints, what I would be interested in is how many edges do I have in my hypergraph? So how many subsets, roughly? I don't need a precise count, but I would like to know, is this linear, quadratic, cubic in n? Okay, and it turns out that Shatter functions are a very good tool to try to estimate those orders of magnitude. So let me introduce them. Let me define them. So you take H, a set system, on X. So you can think of X as being the integer from 1 to n. Usually it doesn't really matter. And you can define, so for any subset of X, you can define the trace of H on S as all the intersection of the edges of H with S. Okay, so if you're familiar with graph, it's not exactly the same thing as induced subgraphs. Okay, in this case, what we would get would be all the edges that are supported by S, as well as all the vertices of S. But if you have if your set system here is just all the edges, you would collect simultaneously edges supported by S and also the vertices of S that are involved in maybe some edge outside S. Okay. So it's another hypergraph on a smaller set of vertices. And the Shatter function fh of k is defined as you just look at the largest possible such trace. Okay, so you look at the size for S in X, size of S equal to k, of the size of this hypergraph, the trace S. Okay, so again, if you're thinking in terms of graph, this amounts to, this count up to some additive terms, this count how many edges can you find over k vertices. So it's a kind of local density, right? How dense can it be locally? If you're looking at this situation, it's, well, if you only take k points, how many subsets can you select out of those k points using disk or half space or unit disk? Okay, so it's a measure. If you're thinking in terms of subset of the discrete cube, you're basically looking at, you choose k coordinates and you project all your subset along these k coordinates, and you're looking at how many points you have in the projection. Okay? And so of course, if you look at fh of n, this is the size of h. I mean fh of size of x, that's the size of h, right? Because you have only one trace. But so somehow this function looks not only at the size of your set system, but also at how this grows when you take larger and larger traces. And there's a very interesting phenomenon that goes on. If you give me one value of the Shatter function, if you give me a non-trivial bound on one value of the Shatter function, this restricts the asymptotic growth. So a non-trivial upper bound on a single value that restricts its yes?
Can I ask, when you say H thought of as a subset of 0, 1 to the n?
Yeah.
Do you mean also including possible edges in between?
No. What I really mean is x, assume x has size n. So you can associate with every element of x one of the axes, one of the coordinates in 0, 1 to the n. And now you map every subset to the point where the coordinate is 0 if the subset has this element and 1 doesn't have this element and 1 otherwise. Does that make sense? Yeah. Okay. So then I just look at subset of vertices.
You just mean the incidence vectors?
Hmm?
You just mean incidence vectors?
Incidence vectors, yes. I mean bit strings. You can think of subset of x as bit strings, saying you number the elements of x, and for each element you put 0 if it's not there and 1 if it's there. You get a bit string, and you can think of it as a coordinate vector. And
but then maybe I'm confused. What do you mean by hypergraphs?
Hypergraph is just it's a set of subset. So if x is 1, 2, 3, and 4, I could have a hypergraph that would be 1, maybe 1, 3, and 1, 2, 4, for example. So it's really a subset of all possible subset of. So very unstructured. There's.
So can I ask now?
Yes.
So this non-trivial upper bound on a single one, so it means fh of 10 is less than 2 to the 10.
Yes.
2 to the 10 minus
Yes.
2.
So.
What? Restricts the asymptotic mode.
Yeah. So fh of k strictly less than 2 to the k. So this is what I mean by a non-trivial bound. So the maximum value of this is 2 to the k, right? That's the maximum number of subset you can have over k vertices. If you give me that it's less than that, then for any n larger than k, fh of n is at most, so I equals 0 to k minus 1 of binomial ni. And in particular, if you look at what happens when n goes to infinity, this is polynomial. It's at most n to the k minus 1. It's order of n to the k minus 1. So either your function is always exponential, or it drops to polynomial. There's a dichotomy going on. Okay, and this is often called Sowers Lemma. It was also discovered by Vatnik and Chervonenkis. And Scheller and Pearls. Okay, so if you heard about the Vatnik-Chervonenkis dimension of something, it's say this is the starting point of it. It's very useful in learning, for example, because in learning you're trying to manipulate. You're basically interested in learning a hypergraph, and this tells you essentially how the small subset look like, how the projection on a few values look like, on a few points look like, and if there's a bound on how messy they are, that means you're basically dealing with a hypergraph that has a polynomial number of edges, and so they are easier to learn, for example, in their terminology. Okay.
So just to be clear, when you restrict it to S, you're saying the set of all configurations where you can only be you can only have ones on the subset S.
So when I restrict it to S, where?
H
Here?
Restricted to S. Right?
Yes. So which are you thinking in terms of subset of 0, 1, n?
Yeah. So the configuration is 0 outside of S.
No. What I really mean is you have. Yeah. So you project on these coordinates, and you forget about the rest.
Okay. So what is E then?
So E is a subset. So E is an element. So
okay.
E is an element of X, so that means that E is contained in X. And I take the intersection. So really whether elements outside S are in or out is not relevant. So you can do this. So there's all this thing, and so this was from the early 70s, so it's not new. It's been used over and over again. It turns out that you can define a similar Shatter function for other type of objects. All that you need is to have a set of objects that is defined by atoms, elements of X, where you have a mechanism for induced subcollections. Okay, if I choose a set of atoms, I can look at traces of my object. So here's another example. Permutations. So what you can do, you can think of permutations as total orders. And now if I have a set of total orders on the element from 1 to n, and you give me k elements, I can look at all the induced suborders on those k elements. Okay, and that can be, I can think of this as the trace. So see a set of orders on X, and C sub S is the induced orders on S. And you can do the same. You can count, you can, given a K, look at how many different orders can you induce on K element. Okay, and you can look at FC, the same. And perhaps you heard of Condorcet paradox. Okay, so you know that election systems are flawed, right? They're hopeless. There's a theorem telling you basically that arrow theorem, that if you list the requirements that should be reasonably expected from an election system, it doesn't exist. Okay, so what do we mean by that? It means that, for example, we're thinking of an election system as you offer n possibilities. You ask every voter to rank them, so to give a total order. And then you try to turn this set of n permutations into one single permutation that somehow represents what the majority wants. And a very naive approach would be to say, well, let's look at two candidates I and j, and let's look at whether a majority of people prefer I over j or j over I. So for every voter has a permutation, so every voter compares I and j. So you can perhaps take the majority. And it turns out that this doesn't work, because it could be, for instance, that you have 3 candidates, and maybe there are only 3 permutations that people choose, and it's these 3, and maybe 1/3 of the voters choose this, and 1/3 choose this, and 1/3 choose this, which means if you look at 1 and 2, there's 2/3 of the candidates that prefer 1 over 2. There's also 2/3 of the candidates that prefer 2 over 3, and 2/3 of the candidates that prefer 3 over 1. So this is not an order, it's cyclic. So that's Condorcet paradox. And for a while, a question that people interested in voting system were thinking about is the following. Assume that you now restrict the set of choices so that this rule works, so that you don't offer the voters all possible permutations, but you offer a restricted set of permutations, so that when you apply the majority rule, it's always transitive, so it always gives you a permutation. How large can the set of choices be? Wow. Okay, so of course this exists. If you offer only one choice, it works. Okay, so there has to be a largest number that you can offer over n candidates. And it turns out that if you have a system that allows this system satisfies this. If 3 is less than 6, And so Raz proved that this alone implies that your number of permutations is at most exponential in n. Using, which is reminiscent of this. So okay. So anyway, just to say, this kind of phenomenon occurs not only for hypergraphs, but you can think of it for other type of combinatorial objects. And it seems relevant. Okay, so now one question you could do is, so if you try to apply this, for example, to points on half planes, Andreas, are you teaching Radon's theorem, Radon's lemma? Okay, so Andreas is not teaching the following statement, but he could. If you take 4 points in the plane, there's always a way to partition them into 2 parts that intersect. Okay. That whose convex all intersect. And 4 points in R2 can be partitioned into 2 parts whose convex all intersect. This is okay, and that implies that for half spaces, for half planes, f h of 4 is less than 16. Okay, because if it's impossible that there is a half plane that intersects these 4 points in exactly these 2 points. Why? Because if this were true, that means that this half space has to not contain this. So the complement of the half space that you're looking at must contain these 2 points, so the complement must contain this entire segment. So your original segment should not be able, your initial half space shouldn't be allowed to contain this point, but it does. Okay, and same here, you cannot get only this point, or you cannot get only this point, these 3 points. Okay, and so with Sowers lemma, you get that fh, that h is big O of number of points to the cube. Because we can apply this with k equal 4. This bound is not sharp. Okay, if you have n points, how many different ways can a half plane intersect those n points? Well, you can always move your so start with a half plane that intersects your point in a certain way. You can always translate it until so my half planes are closed. So I can always translate the half plane until it contains 1 point on its boundary. And I haven't changed the intersection. Then I can rotate it until it contains another point on its boundary. Here I'm cheating a bit, but think about the argument. And in that sense, I can always look at only half planes defined by 2 points. So there should be at most a quadratic number of different traces. Okay, there should be only a quadratic number of such half plane. Here I can, using Sowers, I can only prove cubic. But the input of the lemma is that fh of 4 should be at most 15. Here, I can in fact prove better. I can in fact prove 14. So maybe I have some margin to squeeze a bit more. And more generally, here's a question.
So can I ask a little bit?
Yes?
Maybe I missed the step where you prove f values less than 16.
Yes. So let's reason on these 4 points. And the lemma tells me that what I see here is essentially systematic. Always happen. So if I look at a half plane, in the way a half plane can intersect those 4 points. What I'm claiming is a half plane can never contain those 2 points and those 2 points only. The reason is, assume I have H1, that gives me this. That means that R2 minus H1 contains this and that. Okay, where does this point go? It has to be both in H1 because it is the convex hull of these 2 points. It's on the segment joined by these 2 points, and H1 is a half plane. So if it contains 2 points, it contains a convex hull. But it should also be here because it's on these 2. Okay? So then that means basically you should be on the situation where your 4 points are on the boundary and you have a problem. Is that clear? No?
So you're assuming that these are not on the one line, or?
I mean, if they're on one line, you can argue similarly. If they're on one line, you cannot select these 2 points with a half plane without getting this point. Okay, so there will always be at least 2 of the subset that you cannot get with a half plane.
I mean, at least one of them should that be in there?
No. So I have 4 points. So there are 16 different subsets.
Right.
There are many that I can do. Empty set I can do, or the entire subset I can do. But out of the 16, there are always 2 that I cannot do. And so if my points are not on a line, there's case analysis, but it always goes like this. Okay. So the question here is, if I apply this, if I get this analysis, I can apply this lemma and it gives me some kind of bound, but the bound is weak. But there is some margin that I can squeeze. I actually have a stronger assumption than what the lemma requires. And a natural question is, can I do better? So what is the largest value fh of n can have, given that fh of k is at most m? And I can ask this for any m in k. Okay, I take two parameters, and I would like to have a bound that is more sensitive. So clearly, if m is 2 to the k minus 1, I will only be able to apply this. So this bound is best possible. But now what happens if I get 2 to the k minus 2, 2 to the k minus 3, and so on and so forth? Okay, so exercise. If fh of m is at most m minus, I think it's 1. Let me make sure that I don't get that wrong. Oh, actually m, because of the empty set. This implies that for any n okay, so here's an easy one. If by taking m vertices, m element, you cannot see more than m traces, then your set has no more than m edges. Think about m equal 1. if with one element you can never see two different traces, that means you can't both have an edge containing that element and an edge not containing that element. And that's true for every element of X. That means you only have one edge. Okay? Because every element is either in all the edges or not in all the edges. Okay? Now if you have two elements and you never see more than two, well, there's a pattern there. You can go the other way around. If you have two different edges, there should be a vertex on which they are different. So you look at the trace on that vertex. Okay, one gives you a vertex, the other one gives you an empty set. Now, if you have three edges, well, you can find a vertex that distinguishes between the first two. And now look at the third set. If the third set has this vertex, that means that the trace, so maybe I'm losing everyone by doing it like this. So if you have set x1, a1, a2, a3, if they are, so they are all subset of X. So if x1 and x2 are different, that means there is a vertex that distinguishes them, that is in one and not in the other. So I take this vertex v1, 2 in my trace. Now, v1, 2 may belong to A3, or may not belong to A3. Okay, say v1, 2 is in A1 and out A2. If v1, 2 is also in A3, that means that the trace of A2 and A3 are already different on v1, 2. Okay, so I only need to distinguish A3 and A1. And because they are different, there should be also a vertex v1, 3 that is different. And now if I look at the trace of these three sets on those two vertices, I will see three different traces. Okay? And you can do the same argument in general and you will get this. If you have fh of m at most 2m minus 1, then you can show that fh of n is big O of n. If you're thinking in terms of graph, if your hypergraph comes from a graph, that means is a set of vertices and a set of pairs forming edges, this should be easy. Because in the trace, on m vertices, you will have 1 for the empty set. You will have every vertex will give you also a different trace, which will be just this vertex. So how many edges can you make on m vertices? Well, this minus that. So that's m minus 2. Now, if you have a graph where any m vertices span at most m minus 2 edges, how big are the connected components in your graph? At most m minus 1. Because if you have a connected component of size m, that connected component would span, take neighbors incrementally, and you will, every time you add a vertex to your component, you add an edge. So after you start with one vertex, there's no edge, and 2 vertices, 1 edge, 3 vertices, 2 edges, m vertices, m minus 1 edges. If you cannot find that, and this would already be larger than that. So if you can't find this, that means that your graph has no connected component that is larger than m minus 1. And that means that you can divide your set of vertices into blocks of size m minus 1. On each one, you have a linear number of blocks, and each one creates a constant number of edges. So you get this. So this is in the case where your hypergraph comes from a graph. It turns out that there is a result that tells you that this is a general case. That this proof implies the same bound for all hypergraphs. Okay. Now, there was a conjecture related to that question. by Heinel and Bondi, which is a parameterized version of this. And the way they put it is, if you have fh of k, so here let me rather put m and k. So if you set k to be equal to m minus 1, you get exactly the lemma over there. Okay, so k equal m minus 1, that's Sowers Lemma. It's also known to be true for k equal 2, m equal 4. Golobas
sorry, that's a single case or that's two?
That's a single case. If m equal 4 on k equal 2, this bound for m equal 4 on k equal 2 does indeed imply this bound. And what is known is that this, for n large enough, is necessary in the sense that there are finite, there are a few counterexamples. We managed to build some families of counterexamples, but not for n arbitrarily large. Okay, and maybe a more general way to look at it is to introduce tk. So where is it? Tk of m, the largest integer such that every integer alpha, such that every set system h with fh k less than alpha has fh of n equal big O of n to the k. Okay, so tk of m is you give me k on m. K is the order of growth that you want to have. So you want to have an upper bound that will be quadratic cubic, and you have k equal 2, k equal 3. M is M is how large, on how many points do you want to look at traces. And tk of m tells you the condition that will guarantee, the condition on that size that will guarantee that behavior. Okay, and the question is, what is tk of m? And there was a partial result answer with Otrid here and Cyril Nico. We could prove the following inequality, and here I need the paper. Don't laugh. Tk of m is at least 2 to the k m minus k minus 1 2 to the k minus 1. Okay. So this is a lower bound. what it means is every set system where f of m is at most this has a growth of order at most n to the k. Okay? And the way we did that was by adapting the standard proof of Sowers Lemma, the inductive. And looking at it, I remember we were somewhat disappointed. We didn't know about the Hashnal-Bondi conjecture at that time, but even though we were disappointed, and when you look at the Hashnal-Bondi conjecture, it's even more disappointing. Why? Because this here is of order m to the k, right? As you fix k, so you have a target order of growth. Say you want to prove that your half planes are actually quadratically many. So you set k equal 2, and you wonder, okay, for a given m, what is my condition? And you let m grow. And the conjecture here is that the amount you can allow in the trace will grow as m to the k, roughly speaking. What we can prove is a bound that grows with m for any k. So of course the factor here grows with k, but it remains linear. Okay? So somehow this is not so nice. So the news is that, well, that's life. It turns out that this is wrong and this is almost right. Okay. So the new theorem is that a tk of m. So the new bound that we get is almost, so it's up to a factor 2, so very similar to that one. We get 2 to the k plus 1 minus k minus 1 times m, and then there is some additive noise. Well, which is noisy, but still it's additive. And so this improves this lower bound by roughly a factor of 2. But there's also an upper bound which has the same term. 2 to the k plus 1 minus k minus 1 m. And here the noise is plus 2 to the k plus 1 minus k minus 2. Okay, so the Hashnal-Bondi is false, and the previous bound is within a factor of 2. And these are two consequences. A third consequence, which may interest geometers, is that the way we prove this upper bound, that's what I'm going to tell you for the 10 minutes that remain. The way you prove this upper bound, you can prove that there is no condition that you can put on f h of m that will give the right order of magnitude for points on half planes. So remember, points on half planes, you can prove that the number of traces you get on 4 points is at most 14. This doesn't give you quadratic. Okay? You can read it from there. And if you go to 5 points, you can count how many points are in convex position, and we can find hypergraphs that have no more than that on 5 vertices, but have a super quadratic number of edges. And we can do that for any m. So that means if what you're shooting for is the exact order of magnitude of your geometric set system, it can be already for half plane or half spaces in d dimension, it fails. So I haven't checked all the set system, I haven't checked disks, unit disks and everything. You're welcome to experimented, let me know. But my guess is that if you're shooting, so basically I started looking at those questions hoping that I could have a new tool to measure finally the growth rate in the polynomial realm. The outcome is no. Roughly no, that won't work. You will get polynomial versus exponential, but presumably you won't get very fine constant. So no Shatter condition gives the right order of growth for point alpha. Okay. So maybe roughly this here is an adaptation of an argument by Boris and Conlon, David Conlon, for proving the following thing. If you look at, so for any rational between 1 and 2, there is a family of graphs such that if you exclude those graphs, the number of edges you can have is at most n to that exponent. Okay, so it's so there are many results telling you, if you exclude this, then the number of edges is subquadratic and it's at most this. What they were looking for is what are the this that you can achieve? What are the exponents that you can have? And the answer is any rational exponent can be done. And to do that, they basically look at how the number of edges relates to the minimum degree of vertices after you prune your graph adequately. And from these minimal degrees, they can build certain graphs that have to be in your graph, certain induced subgraph. So that's what we adapt. And this here is a probabilistic construction. So that's what I'm going to describe very quickly. So I guess since I didn't continue to number, this is 2. Probabilistic. So I want to fix M and K. I want to take n arbitrary large. Really large. And I want to build a hypergraph. So the task, build H on n such that two things happen. One thing is that the size of H should grow quicker than n to the k, on one hand. And the other thing is I want fh of m to be at most this number, roughly. Something, let me not. Okay, so I want to have small traces, but many faces. So I'm going to build actually a random simplicial complex. So not just a hypergraph, but a hypergraph that is hereditary. Whenever you have a set, you have all its subsets. So the way I do it is I go through the k plus 1 tuple. So I go through 3. So first I add all vertices. Okay, my vertices is I take on n vertices. I add them. Now I look at every edge in turn and I flip a coin. If I get head, I put the edge. If I get tail, I don't put the edge. Okay, of course my coin will be biased. So add every edge independently with probability P. So P is some quantity that I will tune at the end. So then every time I have 3 vertices where I have the 3 edges, I again flip a coin, and with probability P I put the triangle. Okay, add every triangle when all 3 edges are there, again with probability P independently. And you keep doing that up to subsets of k plus 1 vertices. Okay? And so I do that, and I get a set called k. So that's my hypergraph. It's a random variable. I care about 2 things about this hypergraph. How many edges does it have? And
so do you mean that the largest set could have a k plus 1?
Could have k plus 1. And in fact, if I want to beat this, I need to have many. The only edges that could exceed n to the k will be the edges of size k plus 1. So it should be large. I should have many edges of size k plus 1. So of course I will tweak P so that this happens. But of course I also want the traces to be small. So there's some... Okay. So this gives me a first complex. Now, if you want this complex to satisfy those 2 things, it's kind of hopeless. What will happen is that this condition, you can hope that it's violated on only a few occasions. So then, you define a vertex M tuple as bad if, so M tuple, let me call this M, if the trace of k on M exceeds my something. Yeah, okay, so let's 1 plus M plus Z. So I'm introducing a new parameter now. So when I take the trace on M vertices, I will always have the empty set. I will always have the M vertices. So now I have a parameter which tells me how many simplices I allow in my trace. Okay, and if I have more than that, I declare my M tuple to be bad. And then I simply delete all edges of K supported by a bad M tuple. Okay? And now I have 2 parameters to tune, P and Z. Maybe I should let the people who want to go at this point.
Do you want to delete edges instead
Yes.
of vertices?
Edges are 2 element subsets.
No, faces. If you want, yeah, faces. Or faces of the complex, yes. So yeah, so I first.
So you delete everything except the vertices.
Everything, yeah. So every time you have an M tuple, you delete everything that is not a vertex, a bad M tuple. You delete everything supported by that M tuple that is not a vertex. So of course this will bring down the number of faces of K. but hopefully not too much. And now we have to do some cooking.
Somewhat.
Cooking. So,
What do you mean about-
because I need to tune P and Z so that I compile both so here I will get 1 plus M plus Z. So I want this to be big, okay, and this to be small.
Okay, so you're using essentially what they call the deletion. Logical deletion
Alteration or
I use the Boris method. I asked my question to Boris. And
Here,
Yeah.
so when some base is supported by tuple means the base is subset.
yes, contain a subset. Okay, so what do you use to do this? Well, if you look at complexes on M vertices, there are not so many of them. There's only, the number of complexes on M vertices, there are 2 to the 2 to the M at most. I'm overshooting. I don't care because M is constant. Okay, I'm only worried about what happens when n goes to infinity. Now, out of these, some are good and some are bad. Those that are bad, I know that they have at least this many edges. So they had to succeed a certain number of coin flips to get there. Okay, so the expected number of bad tuples, M tuples, I can do a crude Uden bound, and for each of these I sum the probability that I get one of those bad M tuples. Okay, so it will be this horrible constant time P to something. Okay, and that's something you have to count. It's not difficult, but okay. Now, so let me suggest that I stop at this point, maybe. So, okay, this in a nutshell is the way you can do this probabilistic construction. You want to find hypergraphs that have many faces but still have small traces. You build them in a 2-stage probabilistic construction. First you do this. Okay, so you build your complex up. So every time, by increasing dimension, you first add all the vertices, then every edge you flip a coin. Now every triangle that could possibly be filled, where it's not missing an edge, again you flip the same coin, and you keep going up to dimension k. So k plus 1 vertices. This will likely violate your Shatter condition. What you do is you delete whatever is bad, and now you have your 2 parameters, P and Z, and you try to check whether there is a range of values that give you what you want. And it turns out that what you want, what it gives you, is not that bad. Okay, so I can walk through the computation, but I'm not sure that we should keep people hostage in the room for that. And also maybe you can give it as an exercise for homework. So I wouldn't want to spoil that. Okay.